Okay. So our next speaker is Agniv. He will be talking about optimal top two methods for best arm identification and fluid analysis.
Okay, so this talk will be based on joint work with Sandeep Juneja and Shubhda Agarwal. So I'll first introduce the problem. So there are like k unknown distributions, which we will also call arm, and our goal is to identify the arm. Our goal is to identify the arm that has the largest mean by consuming the least number of samples while keeping the probability of error less than equal to some confidence parameter delta. So now so I'll formally define everything. So there are k arms and they have means like mu1, mu2 to mu k, and we call an algorithm or policy to be delta correct if for every choice of confidence parameter delta and every instance mu1 to mu k, the algorithm stops within a finite time and returns the best arm correctly with a probability at least 1 minus delta. And the problem is to design a delta correct algorithm that has the minimum admissible sample complexity for every instance and choice of delta. And so we are assuming that, so this is a simplifying assumption that distributions, so in all the instances, the arms or distributions are from some single parameter exponential family. And there are some examples of such class of distributions are like Gaussian distributions having unit variance, Bernoulli distributions with the mean in 0 to 1, the open interval 0 to 1. So you can see like both these classes can actually be parameterized only using their mean, and this is also true for any SPF. Like distributions in an SPF can be parameterized only by their means, and we will use the mean of the distributions to denote the distributions themselves. So now we look at the lower bound problem, and this will help us design the algorithm. So first we look at something called data processing inequality. So what that means is, so let's say there is some sample space and I have two distributions over them, P and Q, and there is a function defined over the sample space, G. Then the data processing inequality says that the KL divergence between P and Q is larger than the KL divergence after I apply the so the distribution of the variables g of x after x being sampled from P or Q. So essentially this means I process the random variable x using some fixed rule g, and after that the distance between the distributions can be at most the distributions from which x is sampled from, and this will help us get the lower bound problem. So again, like consider two instances, the red one mu and the blue one nu. Then the KL divergence between the distribution of the observations from mu and from the observations from nu is at least KL divergence of these two Bernoulli events. This is like returning the first term in mu and returning the first term in nu. So by observations from mu, I mean that the algorithm doesn't know what the distributions are. It just sees the samples and the arms it has picked, and based on the history, it just picks another arm and sees another sample, and in this way the algorithm goes on. So one can think the algorithm as this function. So the algorithm is just generating a tuple, like arm and then a reward and then an arm and then a reward, and this goes on till the stopping time. And this is what we call observations. And and this is simply a Bernoulli event, like whether and you can think G as the indicator that the first term is returned as the reported as the best term. Yeah.
The data processing inequality is G a function from omega to omega?
No, G can be a function from omega to R or anything. G is a function from omega to some other set. Let's call it R. And
PGX.
so PGX is just the distribution of GX if X is sampled from P. Yeah. Okay. So now let's say if mu has the arm 1 as the best arm and mu has a different best arm, not 1, then every delta correct algorithm satisfies. So by the KL divergence, by the data processing inequality, we know that the KL divergence between the observations is at least the KL divergence between the events that the first term is returned. And since it is a delta correct algorithm, reporting the first term for the instance mu will happen with a probability at most delta, and the same for nu will happen with a probability at least at most 1 minus delta. And we know that the KL divergence between Bernoulli delta and Bernoulli 1 minus delta asymptotically behaves like log 1 over delta. This gives us this expression that so I just construct the set of all instances nu which has a best term different from that of mu, and this inequality is true for any delta for whatever samples are drawn by the delta correct algorithm. We take I mean since this is true for every new line in this alternate hypothesis, if I take an infimum over all such news, then this inequality must be true, and this we are going to simplify. So the KL divergence between the observations between the samples drawn by the algorithm, this has this nice this decomposes in this nice way. Like we can decompose it as the KL divergence as a weighted sum of KL divergence between the arms of the two instance, weighted by the expected number of samples drawn from every arm, and this gives us this inequality, which is to be satisfied by the allocations done by any delta correct algorithm, and this inequality gives us a lower bound problem. So what this inequality says is that the allocations done by any delta correct algorithm must satisfy this particular property, that it must at least have a log of 1 over delta evidence against the alternate hypothesis of my instance, and this gives us the lower bound problem. So what this implies is that the expected sample complexity for any delta correct algorithm must be lower bound by the value of this optimization problem, where I consider all possible allocations which satisfies this particular property, that it draws at least log of 1 over delta evidence. And the lower bound problem we got, like we have this infimum over all our alternate hypothesis that can actually be simplified, and this infimum is attained at a particular instance, which we call this blue x1a, and so what x1a represents is that it is the instance which is most likely to be confused with the instance mu, now this simplified lower bound problem, like it is easy to see that the solution to the problem O is of the form t star mu times log of 1 upon delta, but this t star is just some constant that depends only on the instance mu. So what all of this tells us is that any delta correct algorithm suffers a expected sample complexity of at least t star mu log of 1 over delta, but t star is just a constant that depends on my instance. And now we define asymptotic optimality of an algorithm by saying that, okay, the algorithm asymptotically must consume at most t star times log of 1 over delta samples. Uh, and so all of this, like we are talking about how an optimal algorithm must allocate samples. Now we should say like when it should stop. So the stopping, so it is proved by Garavier Kaufman in 2016, and later Kaufman couldn't like reduce this thresholds that if we stop using a generalized likelihood ratio based test, so we compute the likelihood ratio as the maximum likelihood estimate of the observed samples and maximum likelihood estimate of the observed samples in the alternate hypothesis. Then any algorithm that stops when this GLLR ratio crosses log 1 over delta plus some smaller order terms which are like of the order of log 1 over delta, then any such algorithm is actually delta correct. Garavier Kaufman actually proved that this GLLR is exactly the minimum of this indexes, like this quantity is IA that we had in the lower bound problem. So essentially any algorithm, any sampling strategy that stops when the minimum index crosses this log 1 by delta threshold, log 1 by delta plus something is a delta correct algorithm. Now the question is how early we can reach into that threshold, and for that we have to look at the lower bound problem again. If we can somehow design an algorithm that whose allocations are converging to the solution of the lower bound problem O, then the GLLR or the minimum index actually grows like n upon t star mu, but t star is like the optimal constant for the instance mu. And then and once the GLLR grows like this, if we stop at this particular threshold, like when GLLR becomes approximately log 1 over delta, then we know that n is like t star mu times log 1 by delta. So such policies are asymptotically optimal. Now we have to see like how to converge to the optimal solution of O, or how to adaptively solve O using whatever samples we are looking at. Garavier Kaufman proposed this track and stop strategy where they kind of empirically solve the lower bound problem at every iteration, and they simply track the optimal allocation after solving the lower bound problem, and then they stop when GLLR meets the threshold. But the problem is, so they showed that track and stop is asymptotically optimal and delta correct because it converges to the solution of O. But track and stop also requires solving this problem at every iteration, and that can be computationally expensive. So we want something easier than track and stop, and later like a string of papers, they propose this kind of algorithms. These are called the beta top 2 algorithms. What they do is at every iteration I have a empirical best arm, and there are some alternate arms, and each of those arms has this quantity index. So what the index gives us is how much evidence I have for each of these alternate arms. Like higher the index, more the evidence I have collected for these arms, and there is a constant beta. So this beta they kind of feed into the algorithm as an input, and with probability beta they just pull the empirical best arm, and with the remaining probability 1 minus beta they pull the arm which has the minimum empirical index, and then they stop when GLLR meets the threshold. They also do some forced exploration, and they prove that this beta top 2 policies are asymptotically beta optimal. And what beta optimal means is that they are optimal, but up to giving a beta fraction of the total samples to the first arm. and this can actually hurt the algorithm's performance. And I think Rousseau in his 2016 paper proved that if we put beta equal to 0.5, then the beta top 2 algorithm is actually too competitive compared to the information theoretic lower bound. So it has a sample complexity of 2 star times log of 1 upon delta. And there is also a unique beta for every instance. There is a beta such that if I feed in the beta, then the beta top 2 algorithm would be asymptotically optimal. Now the question is, and to know this optimal beta, we have to know the instance beforehand. So now the question is, like, can an algorithm adapt to the optimal beta just by looking at the samples, or it can learn the optimal beta? And so to see this, like, we have to look at the first order conditions of the lower bound problem, and it appears that
What is the sense optimal beta means?
So
It's a
okay.
parameter to the algorithm.
Yeah. So what putting in beta does is that it just maintains n1 equal to beta times the total number of samples. It just picks some fraction beta for the best R. Now, sorry. Yeah, the empirically, but like after sufficient exploration, it becomes the best R. Yeah. So doing this, it is actually solving a different problem, and that is O plus this added constraint that n1 is equal to beta times summation A nn. Sorry, this is a typo. This should be summation A. Yeah. So that has a slightly larger sample complexity. So that's what beta optimality means. Now we look at the first order conditions for the lower bound problem, and it turns out that we have this constraint we have this condition that the index of every alternate arm must be equal to log of 1 over delta. I must collect exactly log 1 by delta evidence for every suboptimal arm. But added to that, I have this additional constraint that this ratio of the scale divergence terms, this must add up to 1 for this particular optimal allocation, and it appears that there is a unique allocation that satisfies these two conditions, and that unique allocation actually gives us the optimal beta. And yeah, the optimal beta is given by this condition G equal to 0 and also the equality of these indexes, and we call this G the anchor function. Now instead of like sampling the best arm with a beta probability, what we do is we just look at this empirical anchor function, and if the empirical anchor function is greater than equal to 0, we pull the empirically best arm, and if it is negative, we pull the arm that has the minimum empirical index, and we keep on doing that. So once we do that, so this anchor function has this property that it is actually decreasing in the number of samples given to the empirical best arm and increasing in the number of samples given to the alternate arm. So because of this sampling strategy, whenever I give samples to the empirical best arm, this anchor function comes closer to 0, and when I give samples to the alternate arms, it increases, and so at every iteration, this sample strategy ensures that this anchor function is pushed towards 0, and also just by pulling the minimum index arms, that ensures equality of the indexes, and this itself so the sampling strategy actually converges to this optimality conditions, but proving this in this non-fluid setting is very difficult. So what we instead do is we look at a very simplified behavior of the algorithm, where we assume that all the means are known to the algorithm, and samples, instead of adding like discrete objects, we just increase them like a continuous object, and with that we have this additional conditions, like once the dynamics reaches G equal to 1, it just maintains that, and once index of 2 arms become equal, they stay equal because of this minimum index pooling strategy. And we construct this dynamics using the implicit function theorem. Like we can show that there is a set of, so yeah, I haven't added the ODs into the slide, but we can show that the number of samples to every arm increase by a system of ODs, and we can actually show that the proposed anchored top two algorithm converges to the optimal allocation in a constant amount of time with respect to this log 1 upon delta in this simplified fluid setting. Now, how does this help? Yeah. Yeah.
What's the difficulty? Why can't you simply go to one and sit there?
Okay, so yeah, I'll tell that in the next slide. So yeah, so the algorithm doesn't know mu1 to mu_k, but what the algorithm does is this forced exploration. Like at every iteration, if some arm has less than square root n samples, then I'm giving it some samples. So this actually ensures that every arm at some iteration n, like n is larger than some constant, has omega of root n samples, and because of that, the empirical means actually converge to the true mean at some rate. Like I think if it is root n, then it's like n raised to minus 3/8 after a random time of finite expectation. So because of that, like after this random time, all these empirical means are become very close to the true mean. In fact, they're converging. So now the algorithm's behavior becomes very similar to this system. Like it's as if the real means are visible to the algorithm, and it is converging, it is following this dynamics, and it actually converges to the optimal allocation. And after that, it just waits for the GLLR condition to be met.
But that's true for every algorithm.
That's true for?
Every algorithm. If I allow square root and samples
Yeah.
to be collected for that now,
Yeah.
like to say it's sufficiently close, then I can just do whatever I wanted to do with any other algorithm. It's not sufficient, that's why you have to.
Yeah, but the problem is that the expectation of this T0, I mean, so what you are saying is okay, like there must be a time there must be a random time, and that random time must be less than some threshold with a very high probability, and I just stop there and return the best arm. But to know that threshold, you must know the instance. Like if the gap between the arms, yeah.
If you're using this information within the algorithm,
Yeah.
this information is available to any other algorithm.
Yeah.
So that cannot be the only part which makes your algorithm.
Sorry.
Just the dedicating square root and sample for each arm.
Yeah.
And getting a good estimate. If that was sufficient for distinct two arms.
Yeah.
That would have been used to either any other algorithm. But that's not sufficient.
Yeah, but that is actually used in the track and stop algorithm as well for a similar purpose. Like they want to construct a good set. I mean a good time. After that, they want convergence, like so that the empirical means converge to the true mean at some rate. Yeah. So, but because of this asymptotic regime, like okay, maybe your expectation of T0 is very large if the means are close to each other. But if you pick the delta very small, like we are considering the asymptotic regime, where delta is going to 0. So no matter what constant we have there, like for very small, for delta being sufficiently small, it is going to be bigger. Like yeah, we will need more than this samples. Okay. So there is a random time after which the empirical means converge to the true means at some rate because of the forced exploration, and after this random time, the algorithm kind of follows the fluid dynamics, and the anchor function g converges to 0. The index of the suboptimal arms become approximately equal, like they converge to each other and they increase together. And by the implicit function theorem, we can show that the allocation made by the algorithm also converge to the optimal proportions, and hence asymptotic optimality follows. So yeah, so this is just some illustration of the fluid dynamics. So for example, we started the fluid dynamics for this particular instant at some state. Like we gave it some initial number of samples, and And initially it started with a very positive value of the anchor function. And the algorithm just started by pulling the best term, and that brought the anchor function to 0. And once the anchor function became 0, it stayed at this level. And we can also see that because it is pulling just the first term initially, all the indexes are increasing, and after that, like there is a separation between the indexes, and all the indexes eventually become equal after some time, and from this time onward, the algorithm simply follows the optimal proportion.
What do you mean by implicit function implies that the algorithm is optimal? Implicit function is the essential result. So what does it imply?
Okay. So what we have is so we have these conditions, like the optimal allocation is identified by these conditions, and when we analyze the algorithm, we prove that again after a random time whose expectation is finite and order of 1. Yeah, this condition is satisfied up to some noise, and that noise is also going to 0. And we can show that the like if we consider this as a function, like this anchor function and the indexes, this as a vector valued function.
Okay, so then let's say,
Yeah.
so now you have to apply the implicit function to this equation.
Yeah.
But then say that interval there will be differentiable inverse.
Yes.
But what this neighborhood does not say. That we have to analyze.
Yeah, so the size of the neighborhood we don't know, but we can actually but we can actually prove that if this noise is actually arbitrarily is sufficiently small, then every allocation that satisfies these conditions up to that noise actually is very close to the optimal because of compaction.
There is some factor is going to show up in the number of iterations.
That shows up, and that is
That's like a implicit constant.
Yeah, that is an implicit constant. So that is one of the reasons we don't have non-asymptotic bounds on the sample complexity. But if we are studying asymptotic optimality, then it's just having a constant is enough. Okay. Okay. And here are some future directions. So SPFs are very restrictive. Like in real world, the instances are not always from SPF. They can be from the class of bounded random variables, or in fact, they can be Habitat distributions. So in that case also the 82 algorithm. I mean, there is an extended version of the 82 algorithm where we just replace the KL divergence using the KLinf. And okay, I haven't defined what KLinf is. So KLinf is just like a version of this KL divergence, but for parametric classes where multiple distributions can have the same mean. For example, in bounded distributions with bounded support. And computing this KLinf can actually be computationally expensive. Like computing KLinf involves solving a convex problem. Like if we are doing it at every iteration, then it involves solving a convex problem. And can there be a batched version of 82? Like instead of computing the KLinf at every iteration, I can compute them at in batches. Like
KLinf has the root finding. I mean, you can evaluate KLinf to root finding.
Yeah, you can do bisection search and evaluate KLinf, but after you evaluate KLinf, you also have to evaluate this indexes, right? Yeah, this infimum. That is a convex problem. Yeah, and also like the more samples you gather, the harder I think it becomes to evaluate the KLinf because of the dual representation. So like, can there be a batched version of the 82 where instead of finding the anchor function and index at every iteration, we compute it when the iteration is just the square of some integer, something like that. Like we do it only root n times. And can we use this fluid behavior-based approaches for analyzing other pure exploration problems, such as top K-arm identification? So this is studied in a recent paper by U queen and and several other clauses. Yeah. So thanks.
Questions?
So algorithms like the Thomson sampling, where do they fit?
There.
Where do they fit in this framework?
So for Thomson sampling, you need a prior over the. So yeah, here we don't assume any prior over the SPF class. Yeah. But for example, the beta talk to algorithm they assume that there is some prior information about how the instances are coming, and that somehow helps them guess what the optimal beta is. Yeah.
So let's make this speaker once again.